1 radian is the measure of an angle. You already have one way to measure angles, degrees. And the hardest part about what we do today is you guys will want to ask the question, why radians? Like, what's the purpose of this if I can already measure all of my angles in degrees? And it's kind of like a hard buy-in at the very beginning. Why take the time to learn a whole nother measurement when we're already pretty proficient at measuring in degrees? Okay. The key here is you're going to use radians later on if you take another math class. Some of you will go on and take Algebra 3. Some of you, maybe in college, you'll have to take a college algebra class, and you'll likely see radians again. And some people will argue that radians is a better measurement than degrees. Degrees is kind of like this man-made system. Someone decided there were 360 degrees in a circle, and we all just kind of went with that. But why? Okay. The radian is, people who argue maybe it's a better measurement, follows more like of the properties of the circle. It uses the radius, so they feel it's a more accurate way to describe an angle. Okay. So just to kind of be aware, like in the beginning, it will be okay if radians aren't your favorite or you're having some difficult times, putting the two together. That will take us some time because it's brand new. So 1 radian is the measurement of angle in standard position. So we have an initial side on the positive x-axis. The terminal side intercepts an arc. So think about an arc. You talked about arcs in geometry. They're the outside curve of the circle, just not like usually the whole circumference. It intercepts an arc that has the same length as the radius. If you're intercepting an arc that has the same length as the radius of your circle, that's 1 radian. So we'll look at an example or an animation, and I'll walk through it a couple of times describing it, and then I'll let you watch it one more time, and I'll ask you a couple questions from the animation. Okay. Oh, that's my radius, and I'm drawing a circle. Okay. So there's my radius. I'm going to take my radius out of my circle, and now we're going to bend the radius to fit the curve. So there's the arc. That green angle, that's 1 radian. So that's what we're talking about, the angle that intercepts that arc. 2 radians and 3 radians is almost half the circle. Pi radians is exactly half the circle. Think about that. That's 3.14. You needed just a little bit more. If pi radians is half the circle, double that to get your full circle. 2 pi is a whole circle, or 1 revolution. So again, we're going to watch it one more time and we'll talk about it. Watch the animation and think about the definition. You have a radius and you draw a circle. Okay, so you have some specific radius. Take your radius outside and lay it on your circle, creating the arc with length r. This angle that intercepts those endpoints of that radius on the curve, that's the radian. There's 2 radians. There's 3 radians. You're almost half your circle. You need a little bit more. 3.14 or pi radians is exactly half your circle. If pi radians is 180 degrees, then 2 pi radians is 360 and makes a full circle. I'm going to have you watch it one more time at the very beginning, and what I want you to focus on is that very first radian. Could you estimate the first radian in degrees? So about how many degrees are in the first radian? Right here. How many degrees is that? Anybody want to take an estimate? Eric, you say? 60. Kylie, you say? 60, 70. Okay. Yeah, those are great. Actually, if you think about it, you can get a little bit more than 3 in 180 degrees, correct? A little bit more than 3 radians. So if the radian was 60 degrees, 3 would be exactly 180. So it probably has to be a little bit less than that. So Sahil, you're saying maybe 50, 55. it's actually 57. So 1 radian is about 57, I think it's 0.3 degrees. Okay, but you guys were right to say 60, 70, something like that. Okay. Okay. Does anybody have any questions before we leave this slide that has the animation? When we measure an angle in radians now, we're going to be using this idea of the pi radians that you see right there. That's a huge part of how we'll measure in radians, and also that 1 revolution is 2 pi radians. So we'll use those things to help us talk about angles. Okay. Also notice at the bottom of the screen there's a web address. So if you ever want to watch the animation again, you could type in the web address from the notes online and you could watch the animation there. Okay. We're going to write some information in terms of how we're going to convert from degrees to radians in our notes. The conversions are going to be really helpful, especially in the beginning when you're first working with radians. If you're really uncomfortable in radians, you can do some work in the beginning where you take something from radians, you turn it into degrees, you think about it in degrees, and then you put it back into radians. I think that's okay in the beginning, but I do want to say here at the beginning of our lesson on radians, I want you to move towards doing stuff in radians without having to do the conversion first and then put it back into radians. So your goal at the end of the chapter, after we practice and practice and practice, is to be able to work in degrees and in radians separately without always having to convert one or the other. Now notice at the top of the screen I have 2 equal or equivalencies right there. We're going to fill those in. Can somebody from the animation tell me one thing you know about degrees equaling radians in terms of numbers from the animation? How many degrees equals how many radians? Faith, you say?
Well, was it like 57?
Okay, so we could say 57.3 degrees is equal to 1 radian. I think the only argument that like 57.3 equals 1 radian, we might not want to use that for all of our conversions because I probably rounded 57.3, right? Like I kind of just said, oh yeah, it's actually about 57.3. So what's another equivalency from the animation where we would be using exact values without rounding? Besides the 57.3 equals 1 radian. What else did the animation tell us? Faith, you want to give it a go again?
Was it 180 degrees equals 3.14?
Yeah. 180 degrees equals, and I'm actually going to use the number pi. So 180 degrees equals pi radians. We're going to use that one because here we're not rounding. We're not even saying 3.14. We're going to leave it in terms of pi. So we're using its exact values. We're going to use that to be helpful with our conversion factor. And when I talk about conversion factors, it's the same thing that you use for like measurements. So like when you want to change something from like inches and feet, don't you think about like 1 foot equals 12 inches? And then you either multiply by 12 or you divide by 12 to change, okay? Or do you use anything in science to go from inches to centimeters? Does anybody know the equivalency from science class?
Conversion sheets, like
Oh, okay. So there's different conversion sheets you might have in science. Okay. It's the same idea. We're just changing the units and we're talking about angle measures. So we're talking about degrees or radians. Okay. So to convert something from degrees into radians, think about if you have something in degrees and you're going to multiply it by a conversion factor, which is some kind of fraction. We're going to use this equivalency, 180 degrees equals pi radians. Do we want to put 180 degrees over pi radians or pi radians over 180 degrees here? If we want to get out of degrees and into radians. Which way should you write it? Degrees is here in the numerator. That's what you're working with. How can you cancel out degrees? Should you put it in the numerator or in the denominator? You should put degrees in the denominator. So if we want to cancel out degrees and move into radians, okay, here degrees would cancel with degrees and we'd be left with whatever we want in radians. So the key to remember is multiply by pi over 180. It's the same way like if you say, if you have something in feet and you want to turn it into inches, multiply by 12 inches over 1 foot. Then your feet will cancel out and you'll be left in inches. Or if you have something in hours and you want to figure out how many minutes that is, multiply by 60 over 1. 60 minutes over 1 hour. And you cancel out hours and you change it into minutes. If you want to go the other way, if you want to go from radians to degrees, what will you multiply by? So now you want the radians to cancel. Where should radians be in your conversion factor? In the numerator or in the denominator? In the denominator. So we'll put pi radians in the denominator and 180 degrees in the numerator. That way, radians cancels out radians and whatever we multiply is left over in degrees. So we could make a little note to ourselves over here, multiplied by the reciprocal, 180 over pi. Now, you have two options going forward, and you'll be quizzed over this on Friday. You can memorize degrees to radians is multiplied by pi over 180. Radians to degrees is multiplied by 180 over pi. Okay. Know the conversion factors. Or you can think about it more like when we do conversions maybe in science class, or when we do conversions of time or length, and how you decide, in order to make my 1 unit cancel, what belongs in the numerator and what belongs in the denominator. So it's up to you, whichever one you're more comfortable with. Some of us would rather just think about it and make sense. Okay, I got to cancel out degrees, so I'll put degrees in the denominator. And others of us would be just as happy memorizing the information and using it going forward. Okay, I'm not going to dictate to you which way you do it, but you have to know for Friday so that you can convert from one to the other. So let's look at our first example, and you can use your notes to kind of help guide what's going to happen here. We want to convert 150 degrees into radians. You can look above in your notes for specifically what is the conversion factor that I'm supposed to use, pi over 180 or 180 over pi. Or you might think about it more intuitively. I want to cancel out the degrees. So when I multiply by my conversion factor, I would want degrees to be in the denominator. So I'll put 180 degrees in the denominator and pi radians in the numerator. And this way, degrees over degrees will cancel, and I'll be left with just radians. A lot of times we don't even label radians when we're talking about angle measure. We'll just leave it as a number without a degree sign, and then that implies that the angle is in radians. Here's the rest of it. I don't want a decimal. So you did this a lot in geometry when you worked with pi. Leave your answer in terms of pi. So if I were working in terms of pi, one thing I might do is like I could multiply 150 times pi, but I actually don't want to get a decimal, so I'll just write 150 pi. And then the only thing in the denominator is 180, or I could think about that as 180 times 1. So this is really 150 pi over 180. And then I just have to reduce the fraction. So I'm doing a lot of fraction work here. What's nice about both of these is they're both divisible by 10, so that's really like 15 pi over 18. And then 15 and 18 are both divisible by 3, Jace says. So I could reduce those even further. 15 divided by 3 is 5 pi. 18 divided by 3 is 6. So we have 5 pi over 6. Now we want to convert something into degrees. So we'll have negative 7 pi over 6. And again, notice there's no label there. There's no degree there. So we assume this angle is given to us in radians. And if we want to cancel out radians, when we work with our conversion factor, we're going to put radians in the denominator. So that's the pi radians in the denominator and 180 in the numerator. That means that our final answer will have the same units as the numerator, which is degrees. So we'll have degree on that. I'd work with my fractions here. Pi in the numerator will cancel with the other pi in the denominator. If you wanted to, you could go to your calculators right now, and you could do negative 7 times 180 divided by 6. Or you could keep like canceling if you didn't have a calculator. I can cross cancel 180 and 6 are both divisible by 6. So this one will, 6 divided by 6 is 1, and 180 divided by 6 is 30. So I'm just cross canceling there. And then all I would have to do is take negative 7 times 30, which is negative 210. Okay, so I'm almost at this point not even treating it like an angle measure, I'm just multiplying fractions. So I'm thinking about old things that I did back in 3rd or 4th grade. And you should get the same answer, like if you do negative 7 times 180 divided by 6, or negative 7 divided by 6 times 180, you should still get negative 210 in your calculator. Are we okay with that? Conversion? Okay, now the next slide I show you is from your book. You do not have to copy this down into your notes, though you may want to write down the book page number. These are very common angles. And if you look in the first quadrant here, you'll kind of catch on to why these are some very common angles. The numbers in the first quadrant are 30, 45, 60, and then we get up to 90. Those are the same angles that show up in the special right triangles we studied last week. 30, 60, 90, 45, 45, 90. So this chart or this picture on page 472 just shows you like what those angles, those common angles are equal to in radians and degrees. So like a 30-degree angle is always pi over 6 radians. A 45-degree angle is always pi over 4 radians. And a 60-degree angle is always pi over 3. And then as you go around the circle, you're going up by 30 or up by 45 or up by 60 from the quadrants, and you're coming up with some of those same values. So I won't say that you have to memorize this now, but it's good to just kind of be aware of, and you might catch yourself like at the end of this chapter, you don't even have to do a conversion for pi over 3 anymore. You know it's 60 degrees, and that's awesome because you made that connection. If you take Algebra 3 next year, you're probably going to spend some time memorizing these, where you know all the angles and what they match to. Okay, and then you'll also learn other information on that circle. So just kind of be aware of that's something that will pop up probably from here on out in your other math classes, the same circle and these same angles. We want to make sure that we finish our notes, so I'm going to skip the other two conversions and we're going to jump ahead to coterminal angles. We did coterminal angles yesterday in degrees. And if you look back in your yesterday's notes, this is almost exactly the same information that you wrote down yesterday. Okay, one small change. Coterminal angles are angles that share a terminal side. If you're sharing an initial side and you're sharing a terminal side, then you're the same angle. You're maybe just different measures. That definition of coterminal, that's the same from yesterday. Yesterday we said to find our coterminal angles, we'll add or subtract 360. If we're working in radians, instead of adding or subtracting 360, we should add or subtract 2 pi. So all we're doing is we're changing the value that we're adding or subtracting, because one revolution is now a different measure. I will make a note, an additional note. If you're adding or subtracting fractions, you need common denominators. So a lot of the math that you're doing here in section 9.2, day 2, is work with fractions. If you look back at those two conversions we did on the previous slide, we had 5 pi over 6 and we had negative 7 pi over 6 for our radian measure. And if you look around that circle, there were a bunch of fractions with pi's. So we still have to know how to work with fractions, and if we're adding and subtracting 2 pi with a fraction, we're going to need common denominators in order to be able to do that addition or subtraction. Coterminal angles in 360, we didn't have to worry about this because we were just adding numbers with other numbers. Okay? Things change in radians because many times radians are written as fractions. So we'll start with 2 pi over 5. And we want to find coterminal angles. We'll go under the same set of rules as yesterday, which is when you're finding the coterminal angles, you should be able to find one positive coterminal angle, and you should also find one negative coterminal angle. So, 2 pi over 5 is my initial angle measure. Suppose 2 pi over 5, suppose I'm modeling 2 pi over 5. Okay. If I want to be the same angle but a different measure, my only option is to go all the way around my circle and right back where I was, right? And then I'd just be a different angle measure because I'd have an extra revolution. So we're just going to add or subtract the full revolution, which in radians is 2 pi. So let's add 2 pi to this. Do not fall to the temptation of saying your answer is 4 pi over 5. Because this 2 pi is really like 2 pi over 1. So here's where that extra statement. In order to be able to add these, you need common denominators. So a good common denominator for these would be 5. Multiply this by 5 over 5. And I'm really saying, let's take 2 pi over 5 and add 10 pi over 5. That's the same as adding 2 pi. And now I can add across in my numerator for 12 pi, and I can keep my denominator 5. That's one positive coterminal angle. To get one negative coterminal angle, subtract 2 pi. So I can go back and say 2 pi over 5 minus 2 pi. But then I need common denominators, so that's really 2 pi over 5 minus 10 pi over 5. And that gets me negative 8 pi over 5. Notice I didn't do as much work as I did on the first line because I figured out after this first line that 2 pi was equal to 10 pi over 5. So for that whole problem where I'm working with the denominator of 5, I can replace the 2 pi with 10 pi over 5 if I'm doing coterminal angles. So if I want another coterminal angle, I could just add or subtract another 10 pi over 5. I don't have to worry anymore about calling it 2 pi. Questions about what you see right there?